Hi, I'm going to do a quick introduction on equilibrium, which is the fourth unit of the grade 12 chemistry. So let's think of our grade 11 stoichiometry problems and say you had a question like the one here. If we started with 0.035 moles of our reactant in a 1 liter container, what would the concentration of the product be? Here, because the molar ratio of dinitrogen tetroxide is 1 to 2 to the nitrogen dioxide, you'd assume that the reaction goes completely as written, being all of the reactant is created into the product. You multiply the 0.350 moles by 2, and you get that 0.070 moles exist in the 1 liter container. However, in reality, all of the reactant doesn't completely create the product. There's a balance between having some reactant and some product. If you started with only the dinitrogen tetroxide, you would get some of it creating nitrogen dioxide, depending on the conditions, but there would be leftover reactant. So what this is the same reaction that we looked at on the last slide, but in reality, what happens if you start with 0.035 moles of nitrogen tetraoxide is that you reach an equilibrium where you have 0.0292 moles of your reactant and 0.0116 moles of your product, which is a lot less of the product than would have been predicted in the last slide. So you could calculate this and give a little statement saying actually only 16.6% of the reactant was created in the product by doing a similar calculation to percent yield that you would have done in grade 11. Here you actually obtain data that you would get experimentally versus your grade 11 theoretical number of 0.07. So we've mentioned equilibrium a few times. Another thing to note is if you started with all of nitrogen dioxide and had this occur in the reverse reaction, you would get the same concentrations if the system was in the same conditions. Doesn't matter if you start with your reactant or your product, you're going to get those same final values. Many reactions actually take place in both the forward and reverse reaction, and they happen at the same time. They just happen at different rates. And when you reach equilibrium, you've hit the point where the forward and reverse rate are exactly the same, so that your concentrations of products and reactants are balanced. And this leads to the actual definition of equilibrium. It's a balance between opposing forces. When you talk about equilibrium in other contexts outside of chemistry, it's finding the balance of opposing forces. It's finding some equal point where one force and the other come together and you don't see any, if we're talking movement, you don't see any movement of those forces. In chemistry, the balance of forward and reverse reactions, and there are 3 different types: solubility, phase, and chemical. In interest of time, we're going to focus mostly on chemical in this course and unfortunately not get to details about solubility and phase equilibrium due to our time constraint. So if you're looking at this concept of equilibrium, I always use a metaphor of an escalator. So say you have a down escalator at the mall and you're excited to run up the escalator. Running up the down escalator, I'm sure everyone's done that at some point. If you go slower than the escalator is bringing you down, then you are going reverse. Your back would be coming down. If you go faster than the elevator is bringing you down, you can in fact go up the down escalator. However, you can find a balance where if you're walking at a certain rate and the escalator is taking you down, it doesn't look like you're moving at all. Someone from the other end of the mall that's looking at the escalator would just see you kind of bobbing up and down, but not actually going up or down the escalator. This is dynamic equilibrium. This is you're moving at a very tiny level. Your feet are going up those stairs, and the the escalator is moving at that same rate. The forward and reverse rates are equal, and microscopically both are doing things, but at the macroscopic level, your actually displacement on that escalator, is not changing. So this is very similar. Let's look in very quickly at solubility and phase equilibrium. So solubility is when both crystallization and dissolution are occurring at the same time. So you have a solid in solution, and you have, let's say this is sodium chloride, the smaller sodium molecule that is surrounded by the water molecule may run into the solid at the bottom, and because of the ionic charges actually stick to the other negatively charged chlorine, but at that same rate that those cations are joining, cations from the solid are leaving and being dissolved and surrounded by the water molecules. When you reach the solubility equilibrium, this is occurring at the same rate. Some of the ions in solution are becoming solid, and some of the solid is becoming ionizing, going into that solution. Those collisions are always occurring, which is causing this to occur. It says you need a supersaturated solution, because if you just had a solid that wasn't enough to saturate the solution, then it would just dissolve, and there wouldn't be a solid in the solution for the ions to join onto to solidify. So you need a supersaturated solution to reach some level of solubility equilibrium. Phase equilibrium is the exact same thing. Let's say you have a closed flask here, and in our round bottom flask we have liquid at the bottom and then gaseous molecules at the top, and they're moving around, and when that gaseous molecule maybe hits the surface of the liquid, let's say it's water, the hydrogen bonds from the water that are in the liquid could attract one of those water vapor molecules, and it would attach itself and become part of that liquid. At the same rate, when you reach phase equilibrium, gaseous water vapor would leave the liquid barrier, and you'd have some of the water vapor becoming liquid and some of them becoming gas. And if you reach phase equilibrium, these are happening at the same rate, and macroscopically looking at the flask, you wouldn't see any change. You would see the same amount of gas and the same amount of liquid. Okay. This is just kind of, you could write that double arrow indicating equilibrium for phase equilibrium as well. And it is dynamic when you have them both going at the same rate. Chemical equilibrium. So we're going to focus on this. It's more complex, and it's going to be, we're going to do a lot of calculations with chemical equilibrium. So to define it, it has to be closed. You have to have a closed system so that nothing can escape that system. For example, let's say you go with a natural gas barbecue. If you are burning the methane in the barbecue, the carbon dioxide and water vapor are going to get out into the atmosphere and leave that barbecue. You can't push the carbon dioxide and water vapor together to create methane. There isn't a reverse reaction for the combustion of methane because the system is not closed. You would need a closed system in order to reach some sort of equilibrium. Let's look at the first example that we had, where we have the dinitrogen tetraoxide. You would say that if we started all with that reactant, they would start to decompose and create the nitrogen dioxide and eventually reach this equilibrium. So this is a concentration versus time graph, and it looks like you kind of reach equilibrium around the 20th second, where you get these concentrations from your reactant and product existing together in your closed container. Here you could do different things with temperature to force the reaction one way or the other, and we're going to talk about more detail of how temperature affects that system. But we're going to just quickly go over 4 of the properties of an equilibrium system. I've probably mentioned all of these before. So it must be closed. You can't have any of your species involved in the reaction leaving the system. You also need to have constant temperature so that energy would be enclosed in your system as well. The forward and reverse reactions in equilibrium will be equal. So that here are these two graphs, and you can see in this one you have what looks like a rate law equation. We're going to use the rate law to actually define our equilibrium constants in later lessons. The third property is the concentration of reactants are constant at equilibrium, and in fact all macroscopic properties, so the color, the pressure, the pH, all of those sorts of properties will also be constant at equilibrium. The same equilibrium state can be reached from starting with all reactants or all products. If all of your other properties mentioned in the third one are the same, and you start with a certain concentration of reactants, you're going to get the same equilibrium whether you start with reactants or products. This highlighted at the bottom, the dynamic change at a molecular level but no change at the macroscopic level is what I've mentioned a few times. You have in solubility equilibrium, ions in solution becoming solid, solid becoming dissolved in the solution. In phase, you have gas and liquid going in and out. But if you looked at those, you wouldn't see a change. So in chemical equilibrium, it's the same thing. You have constant concentrations of your reactants and products, but in fact they're colliding, and maybe a couple of the molecules are reacting to create more product, but then a couple of the products are reacting to create more reactant. They're just happening at the same rate.